So this is definitely a harder optimization problem. You don't see trapezoids described in semicircles often, and also there's not much to work with. You have to come up with your own equations through clever setups. Okay, so some of the tricks I show you here can be applied to these kind of harder geometry problems. Okay, we have to come up with your own equations. Let's start filling in this drawing. I already set it up for you guys here, but there's more we can do. So the diameter of the semicircle is 6, which means on both sides it's going to be 3. And there's one more thing we can do. Where they intersect, we don't know where they intersect to give you the maximum area, but we can label them in more general terms and call this point x comma y. And on the other side, assuming it's symmetrical, okay, this is negative x, y. And you'll see in a bit why that will be very helpful. Okay, great way to start this problem. So here we go. Let's start off by coming up with the equation for the semicircle. Might as well see this as a full circle. In that case, circle, center at the origin, radius of 3. Okay, so that's a circle. All right, now our goal is to maximize the area of the trapezoid. So we'll do that by coming up with the equation right here. Remember, the area of the trapezoid is h over 2 times base 1 plus base 2. Okay. Before I move on, I should do something as well. Let me figure out the equation for the top half of the circle. The way to do that is to get y by itself. I'm going to subtract x squared to the other side, square root both sides. Normally, you would have plus and minus, but thing is we only want the top half, so we remove the negative sign, which just leaves a positive half of it. Okay, so now we can work on the area of the trapezoid. A lot of variables here. Let's bring this up. Some things we know. We know the base of one base of the trapezoid, the longer base, running along the diameter of the circle is 6. So let's go ahead and fill that in. So oops. Okay, so I'm gonna write it out here. Okay, the rest we have to be kind of clever. The height of the trapezoid, okay, you see how it touches the xy coordinate of the semicircle as well? Well, height is vertical, and that's measured by the y value. So you might as well call this the height, the y, okay? And y expression we already found, y equals square root 9 minus x squared. So you can go ahead and substitute that expression for h, for the height of the trapezoid, okay? Let's go ahead and do that. So I'm gonna factor out the 1/2 like this, and then write in that expression like that. Okay, last but not least is the first bit, the shorter base. And we have to come up with an expression for that as well. The way we can do it is if this point is x and this point is negative x, okay, or at least the x values are, then we can come up with an expression where the base, the shorter base, stretches from negative x to x. So equation for that distance is x minus negative x, which is 2x. Go ahead and write it there. So we have this expression. Now we can go ahead and simplify this somewhere before we use the first derivative test on it. I'm going to go ahead and distribute the 1/2 to this factor there. And so I will get x plus 3 times square root 9 minus x squared. We can officially get started here. Okay. Remember, optimization problem. What are we maximizing? The area of the trapezoid. So we are going to use the first derivative test. Okay. Let's go ahead and do that. But before that, you notice we have to use a product rule. Let me set that up. I'm going to take this derivative kind of quickly. Okay. So now the derivative will be this triangle. Twos will cancel out. So we have x plus 3 x over square root 9 minus x squared. Okay. We're gonna have to take care of the fractions here. And actually, now I think about it, a quick math trick if you want. Okay, because eventually we're gonna have to set this equal to 0 to use the first derivative test. So you can multiply both sides by square root 9 minus x squared. And that way, we no longer have this fraction, okay? So you distribute that, then you'll have 9 minus x squared here, minus, I'm going to distribute the x as well here to get x squared minus 3x. Let's go ahead and factor out the negative and rewrite some of the terms here. This looks like it can be factored. I think I messed up setup, but it'll work out. Is that right? Oops, switch to signs. There we go. Cross multiply, add together, you will get plus 3x. So my factor, full factor form. Oops. Okay, you can obtain your zeros to set up your first derivative chart. So -3, 3 halves. Let's test 0, which in that case, this will give you negative, positive, negative. Okay, so that's positive. Okay, if you test 1, oh wait, sorry, you can't test 1. Test 2, okay, 4 minus 3, that's positive, positive, negative, test positive. Okay, that's negative. That would be negative as well, I'm pretty sure. So based on the first derivative test, the sign changes from positive to negative at x equals 3 halves, which indicates that is a relative max. So now, to solve the problem, our goal is to find the maximum area. And so you want to plug it into the area of trapezoid. Let's use this one right here, because that's in terms of x. So you go ahead and punch it in, or I'm sorry, plug it in and then punch it in the calculator. So what was it? X, oh, I forgot. Okay. Plus 3 times square root 9 minus x squared. Okay. Little calculator work. We'll get 11.69. Okay, there you go. So difficult one, but some valuable tricks to help you do this faster or to get your next step. Okay. All right. Thanks for watching.